First of all, thank you very much for the organizers to this very nice meeting and for the great training school that we had at ESO Friday and Saturday. Was a great thing. I think first time I saw that in a conference, and I think it's a great idea to spread the knowledge. I'm here, as you can see, I'm the last author there, so it means that I'm not very relevant, but I'm just a messenger there. And on behalf of my PhD student, Jorge Martins, who is back in Portugal, and he's working with Nuno and Pedro, who are actually driving this project. And I insist to Jorge to come here and present his work. I said, look, I'm busy writing my thesis. And he sent me a picture. It doesn't look like he's that busy, but I mean, I'm happy that I got this slot to present his work. Okay? So we have seen this, that planetary formation is a diverse and very common phenomena, and today we know close to 4,000 exoplanets in immense diversity in size and densities, and this is a very nice poster from Martin from Slovakia, and representing 500 planets, right? It's nice that you put a face on them. That's the nice part of it, and just representing the temperature and density just to see the diversity. So there you have Earth and Venus in a small circle there. Okay. Now, if you put there you have seen this many times, and you're going to see more and more of that. So you have seen this, now if you put in there in radii, and now in terms of energy received by those planets, right? And you look for the ones who are close to us in size, and also in terms of energy received, we see that they're abundant. Okay, not yet, but Kepler, radio velocity surveys, and simulations, they tell us that they are out there. Okay, but to find them and to be able to characterize, first to find them, we need meter per second precision in radio velocities, and photometric precisions of around 50 ppm, which is TESS, for instance. Okay, so those are the guys that, in the context of this conference, are interesting for us. Of course, we want to know the planetary formation at large, but for this conference, those are the kind of planets that we are interested at. Okay, and this is a representation of the habitable planets that we have so far, and the colleagues there, they calculate this index, which is taking account the size and again the energy received by each of those planets. Okay, Ross is missing there, and once you have those guys, the next step is to do transmission spectroscopy. Hopefully, right? I'm not talking about, this talk is not about transmission spectroscopy. The title is right. It's not transmission spectroscopy, it's reflected light. So the next one is about transmission spectroscopy. But just to make my story short, in transmission spectroscopy, you are probing the external layers of atmosphere, the high atmosphere that is filtered out by the stellar light. Okay? And as you see here, in this plot here, whenever you have a system that has an extended atmosphere, you get a very high signature in your transmission spectra. Okay? If the atmosphere is opaque by clouds or is close to surface, you have no signal in transmission spectroscopy. So that is the challenging that people doing transmission spectroscopy, they have to face. Okay? Now, what we did here, we tried also something that's very difficult. We tried to measure the reflected light of the exoplanets, right? So how we do this? So very intuitively, right, this plot here shows that you are observing a planet, is in quadrature, and you see essentially the reflected light by the day side of the planet, reaching you, okay? And you see, just plugging the numbers there in this equation there, it depends on the albedo of the planet, and the albedo itself depends on the wavelength, the phase function, and the geometrical factors there, okay? So that ratio there is 10 to the minus 6 for hot Jupiters and 10 to the minus 9 for Earth-sized planets, right? And the beauty of this is that the radiation comes and there is bounced back in the atmospheres and the clouds, but also it also penetrates deeper down in the atmosphere of the planet, and sometimes reaching the continents or the rocky structure of that planet. Okay, so that's why you see that technique is complementary to what you can get from transmission spectroscopy. Okay, and if you think that clouds in a planet like Earth, of course it depends on many factors, but in a culture like us, clouds are formed very close to the ground, right? Opposed to thousands of kilometers of transition spectroscopy, you are probing very deep in the atmosphere of that planet. That's why I think this technique is also nice to explore with the mega telescope we're going to have. Okay, so how we did that? So we start with the spectrum, and we do a cross-correlation function just to increase the signal to noise, right? And then, of course, I'm exaggerating here because you don't see the planet in the spectrum, but the planet is there. It's like a small mirror reflecting the exactly the same spectrum of the star, but it is moving, right? Due to the orbital motion, is moving. And for each observations that you take, you divide that by a template, a very high signal to noise template, and you end up with that plot in my left there, right, where you have the planet moving according to its orbital motion there. And then you don't see it, but you scan through possible values of the amplitude of the planet, which is proportional to its mass, and we stack that until you find a signal. Okay, that's what we find for 51 PEG. That's the reflected light signal stacked over hundreds of observations there. Okay, and this all is explained in George's work. Was published in 2015 already. So, and this is for 51 PEG, is a prototype of hot Jupiter, right? So, the next step was, okay, can we do this further, right, to smaller planets? And just to summarize here. So with the CCF, we get real mass, and we estimate the albedo. Okay, but okay, let's go for. So what you want to get is something like this from the albedo spectrum, right? That's what would be the ultimate dream, okay? From instead of one value that we get for 51 PEG, that would be the ultimate dream. But can you do this? So we certainly need a lot of photons, and that could probably come from the LTs. Right, doesn't matter which one, if the ESO or TMT or GMT, and also we can already prototype quite of that with the VLT. Okay, so that's what we did here. We just injected a simple model. Okay, we are just observers, right? We don't know much about physics, so we just took the model from colleagues there, and with different concentrations of alkali and aerosols to see how it changed with albedo, and we inject that into our planets. And those are planets, so 2 hot Jupiters, Neptunes, and super Earth there. And the super Earth, we didn't inject the model, we just put a flat, a gray albedo at 0.2 and try to recover that, okay? And that's what we get if you do this, first with espresso, which is the kind of super harps that is go to first light tonight at VLT, and that's what we get for 51 PEG. Okay, instead of 1 point, we get now albedo spectrum. Okay, and for the 2 different models that we get, and this is for the other hot Jupiter. So we can recover the albedo spectrum for those 2 cases already with VLT for giant planets. Okay. Now, if you go to HIRES, which is supposed to be the high-resolution spectrograph mounted on the LT, the ESO ELT, okay, you get a much higher sort of resolution for this albedo spectrum, okay? And you can recover that thing in 12 hours of observations, okay? And for the situation gets difficult even for the LT. For Neptunes, you have lower, the smaller number of beings that you can get, but you can still recover the overall shape, and coupled with models, you can get some clues of the composition of that albedo spectrum and the composition of the atmosphere of a planet. Okay, so that's what we did so far. And just to summarize, we did that successfully. We do re-observations for 51 PEG. That's what done with a 3.6 meter telescope on Lassidian, or we're using HARPS. And we expand that through simulations with Espresso and future high-res. So we're going to try that very soon with Espresso to see if we can actually get those, that's albedo spectrum with a better resolution instead of just 1 point. And this thing can be applied for smaller planets with a reasonable amount of time. I know that you might be deceived by my title, right? And I always get that, right? Because that's what the public thinks we're gonna deliver, and the SOC believe that when I submit my abstract that I will show about that, but that's what we get now, okay? Okay. So before I finish, because I mean, it's being trend this afternoon, everybody has a advertisement to do, and I have mine, okay? And that's the Observing Planetary Systems 3 ESO next year, and we're going to do exactly what you propose, right? Which is to bring the two communities together, solar system community, and we have back-to-back talks to discuss those things. And have a second announcement, okay, for the young postdocs who want to thrive, I mean, in the future, and work on challenging things, right? I mean, knowing that 70 to 80% of the all ground-based astronomy is going to be doing here in Chile, be done here in Chile, okay? So I'd like to invite you to think about the ESO fellowships for your career. So working for ALMA, or work for the LT, or working for the VLT. Okay, so thank you very much.